Good afternoon, Calc 3 gang. Hope this video finds you healthy and well and hanging in there for the end of the semester. We're almost there. I wanted to take just a minute and talk to you about where we're going as a class. So we're in 13.5 today. We've got 4 sections left. 13.6 and 13.7 form the foundation that we're going to need to be able to do 13.8 and 13.9. If we can master 13.6 and 13.7, 13.8 and 13.9 won't be terrible. So I kind of think of 13.6 and 13.7 as sort of the last mountain range we have to cross, so to speak. And then the last 2 sections involve some heavy theorems, but they're going to be just results that we can use to solve problems that are going to be all expressed in terms of the last 2 sections. So of the 4 sections left, I really want to encourage you to sink some serious time into 13.6 and 13.7. I'm going to have those videos up as soon as possible. I've intentionally going to get them up well before the homework is due to give you time to really work through them and think about them, and that should help a lot as we move towards our final exam. The final exam will be something like we did already for the last take-home. I don't know the details yet, but it will be an open book type exam like before. Well, I don't know about you guys, but the weather today, this is on Tuesday, April 21st, the weather is just amazing, and I've had to resist the call to grab my canoe and head out to Bull Creek. It's been tempting, but I wanted to stick around this afternoon and get you guys going on the next section, give you as much time as possible. So with that said, let's dive in. So we're going to be talking about the curl and the divergence of a vector field. These are operations that you can do on a vector field. Some notation that I want you to be aware of. So first off, this symbol is called the del operator, and I want you to think of it as partial x, partial y, and partial z. It's a symbol that we're going to use just to keep some formulas straight. The way we're going to use it is actually, technically speaking, not quite right. It's called abusive notation when you use a mathematical symbol that's technically incorrect, but it makes things simple. This is very standard. Everybody does this. This is just what our book does. I'm not trying to pull anything crazy on you. But this is called the del operator. And with that in mind, we can now talk about the divergence of our vector field f. And by the way, f in this lecture is going to be a 3-dimensional vector field. I only wrote the component functions with their variables one time because that's 9 variables, and I don't want to write that. So typically I'll write it as p, q, and r, but please don't forget that p and q and r are all functions of the variables x, y, and z. Okay, so the divergence of f, what is it? Well, it's written like this. We typically write div for divergence of f, and then we write it the del operator dot f. What does that mean? Well, when we dot, we're multiplying. That's not quite what we're going to do here. We're going to say, okay, partial x of p plus partial y of q plus partial z of r. And so we get exactly that, partial x of p plus partial y of q plus partial z of r. And so this is just precisely p sub x plus q partial y plus r partial z. We'll say it that way. So a quick example, I've got this vector field f, and let's just compute its divergence. Why don't you go ahead and pause the video and work it out yourself, please, and then you can check with what we do together in just a minute. So you should get 2xy plus 3z squared plus 0, which we'll just write as 2xy plus 3z squared. So that's the divergence of f in this case. So one of the questions that students always have is, what does this mean? And there is actually a nice way to think about the divergence. It has a lot of meanings and a lot of different contexts. We won't get into all of that. I'm going to largely teach you how to compute and then solve some key integrals which have far-reaching applications. But if we think about our vector field f as representing a gas or a fluid, I'll typically think of it as a fluid. and I think of a point P in space. So I've got this point P, there's vectors flying all around. Who knows what they look like? Maybe they're doing something like this. I don't know. And typically speaking, in application, these vector fields actually depend on time. So as time progresses, they're actually moving and changing. You can almost imagine if the wind blew across this, then these vectors might sort of move depending on the way the wind was hitting them. So we're not going to do that here. We're going to think about our vector fields as sort of static. But nonetheless, if you think about it this way, and I think about my fluid being described by these vectors. So these vectors are describing the behavior of my fluid. And I pick a point, P. Then when the divergence of F at my point P is positive, okay, positive divergence, the name kind of gives it away a little bit. It's measuring the tendency of the fluid to diverge, to disperse. So when the divergence is positive, the density of the fluid at P is actually decreasing. It's getting less and less. And so here the fluid is flowing out of P. It's almost like there's a spring and the fluid is just flowing away from that point. All right, that's when the divergence is positive. When the divergence is negative, the density of the fluid at P is actually increasing. It's not diverging, it's getting more and more dense at the point P. And so here the fluid is flowing into our point P. It's stacking up, and there's the density at that point is getting more and more and more. When the divergence is 0, the density is constant, and that doesn't mean there's nothing happening. It just means that the amount of fluid flowing into P is the same as the amount of fluid flowing out of P. So I thought I would draw a picture for you. This is just a rough picture, but let's imagine maybe some vectors shooting out of P. Here's this fluid coming out of P, and the longer the vector, right, that's also telling me the magnitude. Maybe I've only got a couple of little vectors flowing into P, and so it's pretty easy to see if this was the situation that there's definitely more going out of P than there is coming into P. So the fluid is diverging from P, so we expect the divergence of the vector field at the point P to be positive. And then on a similar note, you can probably draw the other picture yourself, but if this thing has a lot more coming into it than is coming out of it, maybe the output vectors look like that. Here you can tell, hey, this is a sink. The density is actually getting higher, so we expect the divergence of F evaluated at P to be negative. So that's the situation. One more comment on this. You can think about the divergence of a vector field as a rate of change. It's capturing the rate of change of the density of your fluid at a certain point. So I want you to think about, in general, the divergence is a type of derivative of the vector field. And it's really important that we realize that when you take the divergence of a vector field, its divergence is a scalar function. Make sure that's clear. The divergence of a vector field is a scalar function. So let's go back and just end this video with one quick example. So in our previous example, we worked out the divergence of our vector field. We got this. I just want you to realize that to interpret it the way we were just talking about, you've got to actually plug in a point. So if we plug in the point 1, 2, minus 1, it's easy to see we get out 7. That's positive, and so we can think about the density of our fluid is dispersing, it's diverging at a rate of 7. And so the larger the number, the more rapidly the fluid is diverging from that point. And then, of course, when it's negative, then you actually have flow coming in. So we'll end this video here, and in the next part, we're going to look at what's called the curl of a vector field.